Welcome to a new video in the series of videos on systems biology, digital twins, and AI. And this video is part of block 1 in the course TBMT 42, but it's also going to be used in some various research projects and consortia. And it's available to be used by anybody who wants to do so. And if you want to find more similar material, here is a link where we have collected all our educational material. So in this particular video, we will assume that the model has already been formulated. And so we have the state space form formulated in one way or another, and it will be an ODE model, so ordinary differential equation model. And the question that we'll tackle today is, or in this video, is how to go from the equations to a curve, to a simulation. So how do we do that? It's not obvious, and typically you cannot find an analytical solution, so you need to have a numerical solution. And this is a big field of itself, but it has matured by now, so that for normal ODE models, it's not at all as much of a problem as it was maybe 2 decades ago, 3 decades ago, something like this. So the basic, most intuitive way of understanding how numerical solutions of ordinary differential equations work is the Euler forward method. So we will have a look at that, and also as the most basic, slightly more advanced version called Runge-Kutta, order 4. And once we have looked at those, we will go on and try to understand intuitively why it's important to have a variable steps, so have a correct step size, and why the correct step size, the length of the correct step size, will depend on certain things, and it will change during the simulation. So typically you want, or very often you want to have a variable step size. So we'll understand why that is the case, and then we'll look at an extension of the Runge-Kutta order 4 that has such a variable step size. And this will introduce the idea of stiff solvers. And then finally, some checks and error handling schemes that you can use if you have a simulation that is crashing. So let's jump in. So we have an ODE, and we want to use the most basic way of simulating it, Euler forward. So we have the XTT, and we have a starting place, x of time equals 0 equals x0. So we know we should start here. And the question is, how do we move on? Well, the only thing we really have is this, but this is a very good thing, because this is the derivative. This tells us at this particular time point, or actually at any time point, but if we insert x0 here, then we get the derivative at this particular time point. And the derivative is the sort of limit of the second, or the ratio dx dt. So what we can do is that we can use that derivative and take a step in that direction, and the length of that step here we call delta t. So basically here the value, not at t equals 0, that's where we started, but at delta t is simply the original value plus the derivative at the starting point times delta t. So step in that direction. So this is delta x. So this is the new value, x of t, which is x at the time point delta t. And here probably the derivative has changed. So here we need to recalculate the derivative, So it might be lower, it might be higher. We need to recalculate it because now we have a new time point. So now we can calculate the derivative again. And then we simply do the same thing again. We start at this new time point, x1, and then we step in the direction of the derivative. And then we have the new value. So that's Euler forward, stepping, calculating the new derivative, stepping, calculating a new derivative, and so on. So why do you need more advanced solvers? Well, it's because when you take this step, if this step is too long, then the derivative will have changed here during this time. So the derivative is changing all the time here. So you need to somehow account for that or check for that. And a way to do that is to use this Runge-Kutta fourth order. And basically, then you calculate the derivative at the starting point, just as in Euler forward. But then you say, let's only step half the way and calculate what the derivative is here. So here we used the first derivative, the Euler forward derivative, and we calculate the derivative here. So f allows us to calculate the derivative, the slope, at half the step size. So we step half a step using the original gradient and recalculate the gradient here. But then what if we would have used this new gradient, d2, and do the step instead? So if we use this sort of updated gradient that is in the middle, what if we would have taken a step from the beginning to the middle with this new derivative? That's d3. So it's sort of a doll in a doll. So we use d1 to calculate d2, and then we use d2 to calculate d3, which is a sort of updated alternative value of what the derivative might be here at d3. And then we say, okay, so this is the sort of one that really takes into account what's happening along the way. So let's take a step, the full step, and calculate the derivative here at the end using d3. So here now we take the full step delta t, and we step in the direction of d3, and we calculate the derivative here. So now we have 4 derivatives, d4, d3, d2, and d1. And they all are somehow approximations of the derivative along this step here. So what is the true derivative? We don't know. But the people that developed this Runge-Kutta fourth order, they said, let's do an average of these. Let's assume that they all say something, and let's weigh them together. And let's trust the 2 ones in the middle here the most. So those guys get the weight of 2, and the other ones get the weight of 1. So in total, there are sort of 6 units. So we need to divide by 6 when we add all of these together. And then this is sort of the average derivative. And this is the one, this is this direction that we take when we do the step. So that's the Runge-Kutta fourth order. So it's sort of made up of this sort of iterative improvements of calculating the derivative. And of course, you can do this more times than 4, but here we do it 4, therefore it's the fourth order. So, and this is the sort of average. So, why is this important? Well, it's because if we sort of have all of the derivatives here plotted in red as sort of arrows, and we step in the direction of the derivatives. If we take small steps enough, then we'll get the yellow curve here, which is sort of a nice looking curve. It goes up, and here the derivatives change to negative, so it goes down. It looks like a very nice curve. But if we take 2 long steps, then already in step 1, we will have gotten the negative value and of the derivative. And already in step 2, we will have stepped so much in the negative direction that we actually get the negative value of x. And then you see it sort of just escalating. And this is basically what happens, or what can be one of the reasons why a simulation crashes. and why you get a very unreliable result, that you take too long steps. So that means that shorter steps are good. So if you sort of have the step size here, and here we have the error. You want to be as low as possible on this error. And the error decreases with the decreasing step size. So going in this direction is good. But going too far in this direction is actually also a problem. And that has to do with the error accumulation. So if you take really, really small steps, then the change in X will be very, very small. It might be in sort of not the first or second digit, but maybe in the 15th or 20th digit. And if you have so small changes in X, then you have a problem that in numerics, you only have a number with 15 digits. So you don't know exactly what it is. You have an approximation of X all the time with 15 digits typically. And those errors that have to do with that, if you take very, very small steps, they will start to add up. So if you take too small steps, you start to feel this fact that you only have 15 digits. So if you take really, really small steps, then you also run into problems. So there is sort of a sort of most correct solution, which is somewhere here. But typically, this most correct solution is probably too time consuming. You probably don't want to do that. You want to have correct enough, but then you also want to be finished in a reasonable time. So this question of what is the right step size, it's sort of, it's not trivial. And especially if the true simulation looks something like this. So this is from the Hodgkin-Huxley type of simulations, this oscillating or bursting behavior that you have in electrically active cells. And here you see that sometimes the derivative is changing very rapidly. So you need to take very, very small steps here. But in other parts, the slope is much lower. So here you can take much longer step sizes. So if you have such a situation, then you have a stiff system. You have sort of different timescales. So you need to drastically change your step size. And then you need to have a variable step size solver that takes different step sizes at different points. So it needs to figure out all the time how long the step size should be. And if you're in MATLAB, you can add an S to the algorithm. So not ODE 15, but ODE 15S. And that will be because it's a stiff problem. And let's just figure out intuitively how this is done. So this is again a whole research field, but the simplest way is maybe to understand the Runge-Kutta fourth, fifth order. So then you use the Runge-Kutta fourth order and the fifth order, both to take a step forward, and then you look at the difference between those two. So Runge-Kutta fifth order is a little bit more accurate. So the question is that difference significant? So you have to compare this difference delta here with some kind of cutoff. And that cutoff is given by two tolerances that you set as settings when you run the simulation. So you need to choose values for those to the algorithm. So you need to choose a value for the absolute tolerance and for the relative tolerance. And the relative tolerance is relative because it calculates this cutoff by taking a fraction of X. So say that X is 200, then your cutoff will, for if this arrow is small enough, will have to do with this value 200. So maybe this relative is 10 to the minus 6. So then it's 10 to the minus 6 times 200. And this could often be enough, but sometimes you have a simulation where you are passing the 0. So then X is basically 0. And then if you take 10 to the minus 6 times basically 0, then you come to a situation where you can never fulfill this constraint. And and therefore you need a sort of absolute tolerance that doesn't depend on the value of x. So typically you need to have good values for both of those. And if it's lower, then you accept the step, and maybe even try to increase the step size. But if it's too big, that means that now we're taking too big steps. So then we need to reduce the step size, and we try again. And if you can't reduce it anymore, typically you have also specified the smallest delta t that you accept. And if you reach that smallest allowed delta t, then you get an error message, or it might even crash altogether. So this is sort of the principle of how a variable step size solver works. So now let's move to the final part of this video, which is basically a hands-on guide. So if you have a simulation that crashes, which sometimes you will have, you might discover that the cost function is sometimes not working, and you trace that back to that it's the simulation that is crashing. You need to know what this can be due to in order to guide your error identification. So it might be because the states, the x's, are diverging towards plus minus infinity. And this in turn can be because a state has become negative. And this because you formulated equations in a weird way. Because you're taking a too long step, as we saw in the previous example. This is when you should improve the numerics, maybe change upstol or reltol. And when you have negative concentrations, so then the equations in reaction-based models typically won't behave well. Mass conservation doesn't work, and the solutions might really start to become strange. So once you have started to get on the wrong side, on the negative side, so you have negative concentrations, which is of course unphysiological, then the numerics often also has problems. But it can also be because of other reasons, because you've misformulated the equation so that you divide by 0 somewhere. So let's identify here a way to deal with the crashing simulation. So we have the original simulation, it's crashing. So what do we do? The first is just to simulate shorter, to figure out how long can I simulate. And if you can simulate for a while, what happens just before this crash? Is it going below 0, or is it starting to diverge and goes to infinity? What is happening? And if you can figure out something from that, then of course you solve the problem and you're happy. But if this doesn't work, if you can't simulate shorter, then maybe you should try a more robust solver that doesn't do this change of step size, just to sort of get some kind of feeling for what's going on. Maybe a Runge-Kutta fourth order, or even an Euler forward, which is like very robust. It produces something. It might not be very accurate, but it produces something, so it sort of doesn't crash as often. At least if you take if you just do a little bit. So can we see any behavior whatsoever? What is it all going on? This is sort of what you are starting to wonder here. And if also this doesn't work, then really start to just look at the right-hand side, look at the f. Can you even calculate the derivatives? And if you can't, maybe just figure out which are the equations in f. So f is typically a vector of expressions. Which are the ones that you can calculate, and which are the ones that you can't? And then you have sort of identified where the problem is. So this is a sort of incremental way to zoom in on the problem and to identify what type of problem that you have. So this was a little crash course in the field of simulation of ODE models. So I hope it will be useful for you.